Alright, so we started talking about proof by cases in the last video, and we gave an example of proving a statement that's true about all integers by breaking it up into the even case and the odd case. Let's try something like that here. So we have, let a be an integer. If 3 divides 2a, then 3 divides a. Remember what this division or divides symbol means. This is essentially saying if 2 times a is a multiple of 3, then a itself is also a multiple of 3. And this seems to be correct, right? 3 divides 12, and also 3 divides 6. So in this case, your a is equal to 6, 2a would be 12. We also have that 3 divides 18, and also 3 divides 9. So a would be 9, 2a would be 18. But how do we know that this is true in general? So if we wanted to try to use a direct proof, we would assume that 3 divides 2a, and we would want to prove that 3 divides a. And remember, by definition of divides, this means that 3 times some integer k is equal to 2 times a. And similarly, we would need to show that 3 times some integer j is equal to 2a. Oh, sorry, it's equal to just plain a, my bad. We're trying to show 3 divides a here for some integer j. Alright, so this is what we're assuming. We're assuming this is true, and we need to show this is true. So how do we do that? If we were to assume this and try to show this, we would need to try to get a by itself here, so maybe try to divide both sides by 2. And what does that give us? That gives us that a can be expressed as 3k over 2, or a can be expressed as 3 times k over 2. So this is almost looking like what we're trying to prove, but here's the problem. How do you know that k over 2 is going to be an integer? Usually at this point we would say, okay, well, since k is an integer, this is going to be an integer. But not every integer divided by 2 is itself an integer. So our usual proof technique is going to hit a wall here. There's nothing we can do to justify that k over 2 is necessarily going to be an integer if all we really know up here is that k itself is an integer. Alright, so this is where it would make sense to try to use cases instead. So I'm just going to repeat here. If 3 divides 2a, then 3 divides a. This is what we're trying to prove. So let's try to use proof by contrapositive, since that's usually our next step if direct proof doesn't work. So the contrapositive would say, all right, this is our hypothesis, this is our conclusion. So the contrapositive says, if, all right, not 3 divides a, if 3 does not divide a, then 3 does not divide 2a. Okay. So in this case, we would be assuming 3 does not divide a, and we would be proving 3 does not divide 2a. Well, what does that mean to assume 3 does not divide a? Well, if we go back a couple of pages in our notes, remember that what we had seen was that when we're talking about divisibility by 3, either 3 divides n, right? Either n is a multiple of 3, or if not, that means that we have to be able to express n as either 3j plus 1 for an integer j, or 3l plus 2 for an integer l. So these essentially are your two cases of 3 does not divide n. Right? This is a case of 3 does divide n. These are your two cases for if 3 does not divide n. We're assuming here that 3 does not divide a. What that means is that a is either 1 more than a multiple of 3 or 2 more than a multiple of 3. In other words, a can be expressed as 3j plus 1 for some integer j, or a can be expressed as 3l plus 1 for some integer l. And similarly, we're going to need to show that 3 does not divide 2a. So we need to show that 2a can be expressed as either 3 times n plus 1 for some integer n, or 3m plus 2 for some integer 2. Whoops, sorry, this should have been a 2 here. this is where our cases come into play. So we are going to prove the contrapositive, but we're going to prove it by cases, and these are going to be our two cases. Okay, so let's try and start writing this proof. Let A be an integer. We will prove the contrapositive. Let's make some space here. We will prove the contrapositive, which states if 3 does not divide A, then 3 does not divide 2A. So we assume 3 does not divide A. Okay. If A is not a multiple of 3, this means one of the following must be true. Either 1, A can be expressed as 3j plus 1 for some integer j, or 2, A can be expressed as 3l plus 2 for some integer l. We're going to prove in both cases that 3 does not divide 2a. All right, so let's do this. Case 1. If 3 is equal to, if A is equal to 3j plus 1 for some integer j, we're trying to show that 3 does not divide 2a. So we're trying to show that 2a can be expressed as either 1 more than a multiple of 3 or 2 more than a multiple of 3. So let's just take this equation and multiply it by 2, because we're trying to prove something about 2a. So 2a is going to be equal to 2 times 3j plus 1. And expanding the right-hand side, this means 2a is going to be equal to 6j plus 2. All right, well, this is looking like our second case over here, right? This is looking like 3 times an integer plus 2. So I can rewrite this one more time, factoring a 3 out of my first term here. 3 times 2j plus 2. Now, since j is an integer, the stuff inside the parentheses 2j is an integer also, which means that 2a is 2 more than a multiple of 3, so we can conclude that 3 does not divide 2a. Right? You can't express 2a as a multiple of 3 if it's 2 more than a multiple of 3. It's just not possible. So this is what we were trying to prove. Great, case 1 is done. Now we just need to do case 2. So in case 2, we start off by assuming that a is 2 more than a multiple of 3. So 3l plus 2 for some integer l. Okay, then in this case we would have that 2a is equal to 2 times 3l plus 2, which is equal to 6l plus 4. Well, this is a little bit weird because we're trying to show that we can express it as either 3n plus 1 for an integer n or 3n plus 2 for an integer 2. So if we factored a 3 out of here, we'd have 3 times an integer plus 4. We don't really want a plus 4 here. We want a plus 1 or a plus 2. But there's a way that we can fix this. What we can do is just rewrite our constant term 4 as 3 plus 1. Because we'd like to have either a plus 1 or a plus 2 at the end, and by writing it this way as 3 plus 1, I can now factor a 3 out of my first two terms. 2l plus 1. And then a plus 1 on the outside. Right? I just factored a 3 out of here, so I get 2l plus 1 times 3, and then a plus 1 at the end. And now this is sort of the n that we were looking for up at the top, right? So since l is an integer, 2l plus 1 is an integer also. And now we've seen that since 2a is now 1 more then a multiple of 3, then we can conclude that 3 does not divide 2a again. Excellent. So in both cases, we were able to conclude that 3 does not divide 2a. So since in both cases 3 does not divide 2a, we have shown that for any a that 3 is not a factor of, 3 is also not going to be a factor of 2a. So we've proven the contrapositive, which means that's equivalent to proving the original statement. So this proof used both contrapositive and proof by cases.